Now, when analyzing algorithms, we looked at the number of operations required to be executed, and based on the number of executions required, we decided on the complexity of the algorithm in terms of runtime. So it's for iterative algorithms, determining that is easy. You just look at the code, you could look at the pseudocode, or if you look at the actual code, if you have it, and then depending on the average case or the worst case, you can determine how many executions of operations are required to complete the algorithm. But if your algorithm is actually a recursive algorithm, so it's a divide and conquer algorithm, in this case, it's not that straightforward to actually count the number of operations required. For instance, you can write the binary search in a recursive way. This is the sorted values to be searched, and this is the search key X you are looking for in your list. And what you do is you find the middle point. 1 here is the left indicator, N is the right indicator. You add them up, you divide by 2, you get the middle indicator. And if that holds, then that equals the search key that you are looking for, then return N, the position. Otherwise, if your search key is less than the middle element, then you have to look at the left half. In which case, you again apply binary search with the same search key to the left half of your sequence, A1 through AM, rather than AN. Okay, notice the difference. Or if your search key is larger than the middle value, then you will confine your search to the right half. In this case, you apply binary search to AM plus 1 through AN, the right half, with the same search key. Okay, so this is the recursive implementation of binary search. Now, when you look at the code, since the function has itself inside it, it's not straightforward to come up with the number of operations required so that this algorithm is complete. So what is the complexity of binary search? It's not that straightforward to answer, but what you can do is if you represent the number of operations required by T of N, if the values to be searched consist of N values, then you can look at either of these cases. Since M is the midpoint, either you are looking at the left half or you are looking at the right half. In either case, the size is cut in half. Okay, so this means to be able to complete this search using N values in your sequence, you have to do one binary search using half of the range, this one or this one. Okay, so T of N is equal to T of N divided by 2 plus 1. Well, this plus 1 actually refers to this, just a single operation. Well, in fact, you can also include this comparison here and write plus 2. It doesn't really affect the result. T of N equals T of N divided by 2 plus 1, or T of N equals T of N divided by 2 plus 2. Doesn't really affect the end result, as we will see later on. But at this point, what we have to do is we have to realize the analysis of divide and conquer algorithms is a little bit more involved than iterative algorithms, because it's not straightforward how many executions of the operations are required. So we are going to leave this here for the time being, and such expressions are called recurrence relations, and we are going to talk about recurrence relations next week. And at the end of that class, we will be able to determine the complexity of such divide and conquer algorithms.